What if I told you that right now, as you're watching this video, there's a very real possibility that you, me, your family, your pets, even the device you're watching this on, none of it is actually real? What if everything you've ever experienced, every memory you have, every sensation you've felt, is nothing more than sophisticated computer code running on some unimaginably advanced machine? This isn't science fiction anymore. This is the simulation theory. And some of the world's brightest minds, from tech billionaires to Nobel Prize winners, believe there's a significant chance we're all living inside a computer simulation right now. By the end of this video, you'll understand why simulation theory has gone from fringe philosophy to mainstream scientific debate. What new experiments are being conducted right now to test if we're in a simulation? And most importantly, what it would mean for humanity if we discovered we're not real. But first, let me ask you this. Have you ever had a moment where reality felt glitchy? Where something seemed too coincidental, too perfect, or too strange to be natural? Keep that thought in mind as we dive deep into one of the most mind-bending questions of our time. To understand simulation theory, we need to go back to 2003, to a Swedish philosopher named Nick Bostrom at Oxford University. But actually, let's go back even further, because humans have been questioning the nature of reality for thousands of years. Plato's cave allegory, written over 2,000 years ago, presented a scenario where prisoners chained in a cave mistake shadows on the wall for reality itself. Descartes questioned whether an evil demon could be deceiving him about the nature of reality. These weren't just philosophical thought experiments. They were early attempts to grapple with a fundamental question. How do we know what's real? But Nick Bostrom took this ancient question and gave it a distinctly modern twist. His 2003 paper, "Are You Living in a Computer Simulation?" wasn't just philosophical speculation. It was a logical argument based on reasonable assumptions about the future of computing and civilization. Bostrom's argument is elegantly simple, yet profound. He presents what's called a trilemma. One of three propositions must be true. First, civilizations almost never reach technological maturity. They destroy themselves before developing the computing power to run detailed simulations of their ancestors. Second, even if civilizations reach technological maturity, they lose interest in running ancestor simulations. Maybe they find it boring, unethical, or simply not worth the computational resources. Third, we are almost certainly living in a computer simulation right now. Here's why this logic is so compelling. If advanced civilizations do survive and do run ancestor simulations, they would likely run many of them. If there are thousands or millions of simulated worlds for every one real world, then statistically, any conscious being, including you, is more likely to be in a simulation than in the original reality. But Bostrom's paper might never have gained mainstream attention if not for one crucial factor: our own rapid advancement in computing and simulation technology. Think about video games from the 1970s. Simple dots and lines on a screen. Now, look at today's games with photorealistic graphics, complex AI, and immersive virtual worlds. In just 50 years, we've gone from Pong to games that are sometimes indistinguishable from reality. If this rate of progress continues, where will we be in another 50 years? Or 100? Or 1,000? Everything changed in 2016 when Elon Musk stepped onto a stage at Recode's Code Conference and made a statement that sent shockwaves through both the tech world and popular culture. 1 in billions. Let that sink in for a moment. One of the world's most successful entrepreneurs, the man behind Tesla, SpaceX, and Neuralink, was saying there's essentially a 99.9999% chance that our reality is fake. Musk's reasoning was deceptively simple. He pointed to the rapid advancement in video game graphics and asked, if you assume any rate of improvement at all, games will be indistinguishable from reality, or reality will be indistinguishable from games. He argued that if we can create convincing simulations, we'll create many of them. And if there are billions of simulated beings for every real one, we're almost certainly among the simulated. But Musk went further than just accepting the possibility. He suggested it might actually be preferable. I think it's one of the most interesting questions, he said. And if we're not in a simulation, then we're really boring. The reaction was immediate and polarized. Some dismissed it as a Silicon Valley fantasy. Others saw it as a profound insight into the nature of reality. But regardless of your opinion, one thing was undeniable. Simulation theory had entered mainstream consciousness. Suddenly, everyone was talking about it. The Matrix trilogy gained new relevance. Television shows like Westworld and Black Mirror explored similar themes. Reddit forums exploded with discussions about glitches in the Matrix. Everyday coincidences and anomalies that people began interpreting as evidence of our simulated existence. But here's what's fascinating about Musk's contribution. He wasn't just philosophizing. As someone actively working on brain-computer interfaces through Neuralink, artificial intelligence, and advanced computing, he was speaking from the perspective of someone trying to build the very technologies that could create such simulations. This raises a crucial question. Are we moving toward creating our own simulated realities? And if so, what does that tell us about the likelihood that we ourselves are simulated? If we're living in a simulation, you'd expect to find evidence in the very fabric of reality itself. And surprisingly, quantum physics, the study of the smallest particles in the universe, provides some of the most intriguing clues. Let's start with the double-slit experiment, one of the most famous experiments in physics. When you fire particles at a screen with 2 slits, something bizarre happens. The particles seem to go through both slits simultaneously, creating an interference pattern. But here's the really weird part. When you try to observe which slit the particle goes through, it suddenly starts behaving like a normal particle, going through only one slit. It's as if reality is rendering detail only when someone is looking. Exactly like a computer simulation optimizing performance by only calculating what's necessary. Think about modern video games. They use something called level of detail optimization. Distant objects are rendered in low resolution to save processing power, and only objects you're directly looking at get full detail. The quantum measurement problem eerily resembles this computational shortcut. Then there's quantum entanglement, what Einstein called spooky action at a distance. When 2 particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This violates our intuitive understanding of space and time, but it makes perfect sense if you think of reality as a computational system where information can be shared instantaneously across the program. In 2024, physicist Melvin Vopson proposed something called the second law of infodynamics. Unlike traditional thermodynamics where entropy generally increases, Vopson suggests that in information systems, entropy can actually decrease. He argues this could indicate our universe operates more like a computational system designed to conserve processing power. exactly what you'd expect in a simulation. But perhaps the most compelling quantum clue is the apparent pixelation of reality itself. At the smallest scales, the Planck length, space and time become discrete, quantized units. It's as if reality has a resolution limit, like pixels on a screen. The Planck length is about 10 circumflex negative 35 meters. Unimaginably small. But the fact that there seems to be a minimum unit of space and time suggests that reality might be running on some kind of cosmic processor with finite resolution. This is why physicists like Tom Campbell, a former NASA researcher, are now conducting actual experiments to test the simulation hypothesis. In 2024, Campbell launched a series of quantum experiments designed to detect whether reality shows computational signatures. These experiments look for specific patterns in quantum behavior that would indicate we're living in a computed reality. While results are still preliminary, the very fact that we can design testable experiments represents a remarkable shift from pure philosophy to actual science. But quantum physics isn't the only place we find suspicious clues about the nature of reality. Here's something that might blow your mind. The universe appears to be fundamentally mathematical, from the spiral of galaxies to the structure of atoms, from the patterns on seashells to the orbits of planets. Everything follows precise mathematical rules. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical concepts perfectly describe physical reality? Unless, of course, reality itself is mathematical, which is exactly what you'd expect if we're living in a mathematical simulation. But it goes deeper than that. Modern physics suggests that information might be more fundamental than matter itself. The physicist John Wheeler proposed it from bit. The idea that all physical entities are information, theoretic in origin. Think about it. Every particle in the universe can be completely described by a set of numbers. Its mass, charge, spin, position, and momentum. These aren't just measurements. They might be the actual substance of reality. We're not measuring the properties of objects. We might be reading their data. The holographic principle in physics suggests that all the information in a volume of space can be encoded on its boundary surface, like a hologram. This implies that our three-dimensional reality might be a projection of information stored on a two-dimensional surface. Sound familiar? It's remarkably similar to how computer graphics work. Even more intriguing is the discovery of discrete, digital-like behavior at the quantum level. Quantum mechanics doesn't deal with smooth, continuous values, but with discrete packets of energy and information. It's as if reality is fundamentally digital, not analog. In 2024, researchers have been exploring what they call digital physics. The idea that the universe is literally a computer, not metaphorically, but actually composed of computational processes. Some propose that space-time itself emerges from underlying quantum computational networks. Consider cellular automata, simple computational systems where complex patterns emerge from basic rules. Stephen Wolfram, creator of Mathematica, argues that the universe might be nothing more than a vast cellular automaton, computing itself into existence moment by moment. If this is true, then every moment of reality is literally a computational step. Your thoughts, your movements, the light from distant star, all of it would be the output of an incomprehensibly vast calculation. But here's where it gets really interesting for simulation theory. If the universe is already computational, then creating a simulated universe wouldn't require simulating physics. It would just require running the same type of computation that's already running our reality. This makes Bostrom's argument even more compelling. If universes are naturally computational, then advanced civilizations wouldn't need to simulate physics, they'd just need to run physics. The computational cost would be manageable, and the number of possible simulated universes would be practically unlimited. But perhaps the strongest evidence comes from an unexpected source: the very technology we're building today. Let's talk about Moore's Law, the observation that computing power doubles approximately every 2 years. For over 5 decades, this exponential growth has held remarkably steady. But what does this mean for simulation theory? If we project this growth forward, the implications are staggering. Today's most powerful supercomputers can perform about 10 circumflex 18 calculations per second. If Moore's Law continues, by 2050, we'll have computers capable of 10 circumflex 25 calculations per second. By 2100, we're looking at computational power that's literally astronomical. But classical computing isn't the only game in town. Quantum computers use the strange properties of quantum mechanics to perform certain calculations exponentially faster than classical computers. Companies like IBM, Google, and others are making rapid progress in quantum computing. In 2019, Google claimed to achieve quantum supremacy, performing a calculation that would take classical computers thousands of years to complete. While this was a specialized calculation, it demonstrates the incredible potential of quantum computing for complex simulations. Meanwhile, artificial intelligence is advancing at a breakneck pace. Modern AI systems can generate photorealistic images, write convincing text, and even create videos that are becoming increasingly difficult to distinguish from reality. We're already creating simulated humans. AI avatars that can hold conversations, express emotions, and even form relationships. Virtual influencers on social media have millions of followers who know they're not real but engage with them anyway. Video game environments are becoming so realistic that sometimes it's hard to tell screenshots from photographs. Games like Red Dead Redemption 2, Cyberpunk 2077, and others feature worlds with millions of AI characters living their simulated lives. But here's what's really mind-blowing. We're not just creating simulated people and worlds. We're creating simulated physics. Modern game engines can simulate gravity, fluid dynamics, particle systems, and even weather patterns with remarkable accuracy. The question isn't whether we can create convincing simulations. We're already doing it. The question is, at what point does a simulation become indistinguishable from reality? Virtual and augmented reality are bringing us closer to that threshold every day. When you put on a modern VR headset, your brain accepts the virtual world as real. Your body responds with genuine fear when you're standing on a virtual cliff, genuine joy when you're playing in a virtual playground. Neuroscience shows us that our brains don't distinguish between real and virtual experiences at the level of neural activity. To your brain, a virtual experience is just as real as a physical one. Companies like Neuralink are working on direct brain-computer interfaces that could eventually bypass our sensory organs entirely. If you can stimulate the brain directly, you could create experiences that are indistinguishable from reality. Because to the brain, they would be reality. This raises a profound question. If we're rapidly approaching the ability to create perfect simulations, and if advanced civilizations would likely develop this technology, then how can we be confident that we're not already in one? Not everyone is convinced by simulation theory. In fact, some of the most vocal critics come from the very field that provides some of its strongest evidence: physics. Physicist Sabine Hossenfelder has called simulation theory pseudoscience and argues that it's unfalsifiable, meaning it can't be proven wrong. which makes it unscientific. She points out that if we're in a simulation, we can't know the true laws of physics. We can only know the simulated ones. Hossenfelder's critique is serious. If the laws of physics in our reality are just programmed rules, then physics itself becomes meaningless as a way to understand true reality. We'd be studying the code, not the fundamental nature of existence. She also argues that simulating a universe down to the quantum level would require computational resources that exceed the universe being simulated, be a kind of computational impossibility. You can't simulate a universe with more detail than the universe itself contains. Other critics point to the problem of infinite regress. If we're in a simulation run by beings who might also be in a simulation, where does it end? Could there be simulations all the way down? This leads to logical paradoxes that some argue make the whole theory meaningless. Philosopher David Chalmers, while not dismissing simulation theory entirely, argues that even if we are in a simulation, it doesn't matter. If our simulated experiences are real to us, then in what sense are they not real? A simulated tree is still a tree from our perspective. This brings up deep questions about the nature of consciousness itself. Critics argue that consciousness might be impossible to simulate. That awareness, subjective experience, and qualia, the what-it's-like aspect of experiences, might require more than just computation. The hard problem of consciousness is explaining why we have subjective experiences at all. Remains one of the biggest mysteries in science. If consciousness can't be simulated, then we can't be simulated beings, regardless of how convincing our reality might appear. Some argue for the existence of philosophical zombies, beings that act conscious but have no inner experience. If we're in a simulation, are we conscious beings having simulated experiences, or are we philosophical zombies? Complex, but unconscious programs that only think we're conscious. Physicists also point to fundamental limits on computation. The Bekenstein bound suggests there's a maximum amount of information that can be contained in any given region of space. This could place hard limits on how detailed any simulation could be. Moreover, critics argue that the rapid advancement in our computing technology doesn't necessarily mean we're approaching simulation-level capability. The complexity of simulating quantum mechanics, consciousness, and the full richness of reality might be exponentially harder than simulating convincing but simplified versions. Perhaps most importantly, critics question whether simulation theory is ultimately meaningful. Even if true, they argue, it doesn't change how we should live our lives. Our experiences are real to us, regardless of their ultimate substrate. But despite these criticisms, simulation theory continues to attract serious scientific attention. Why? Because it makes testable predictions. Here's where simulation theory gets really exciting. Unlike many philosophical questions, it might actually be testable. Scientists are designing experiments right now that could reveal whether we're living in a simulation. Former NASA physicist Tom Campbell has proposed several experiments to test what he calls the virtual reality hypothesis. His approach is elegant. If we're in a simulation, the simulation would need to conserve computational resources, which would show up as detectable patterns in quantum measurements. Campbell's experiments look for evidence that reality is rendered on demand, that quantum systems only resolve into definite states when measured, not because of the fundamental nature of quantum mechanics, but because the simulation is optimizing its calculations. One experiment involves sophisticated variations of the double-slit experiment, looking for patterns that would indicate the universe is calculating quantum states only when absolutely necessary. If reality is pixelated at the Planck scale due to computational limits rather than fundamental physics, these experiments might detect it. Physicist Melvin Vopson has proposed testing his second law of infodynamics by measuring information entropy in isolated systems. If information behaves differently than traditional physics predicts, if it shows signs of optimization and compression, this could indicate we're in a computational reality. Other researchers are looking for bugs in reality, statistical anomalies that shouldn't exist in a natural universe but might appear in a simulated one. They're analyzing astronomical data, particle physics experiments, and even biological systems for signs of computational shortcuts or rounding errors. The fascinating thing about these experiments is that they're designed to be definitive. Unlike philosophical arguments, these tests could provide clear evidence one way or the other. Cosmologists are also joining the hunt. If our universe is simulated, it might show edge effects, strange behaviors at the largest scales where the simulation boundaries might be located. They're looking for patterns in the cosmic microwave background radiation and the distribution of galaxies that might indicate artificial limits. Some researchers are even looking for computational signatures in the laws of physics themselves. If reality is computed, the mathematical relationships in physics might show signs of optimization, formulas that are suspiciously simple or elegant because they were designed to be computationally efficient. But perhaps the most intriguing approach comes from artificial intelligence research. As we develop more sophisticated AI systems, we're learning to recognize the signatures of artificial intelligence and computation. Some researchers are applying these techniques to analyze reality itself. In 2024, several research groups announced they're using machine learning to analyze quantum mechanical data, looking for patterns that would indicate the underlying processes are computational rather than natural. The results so far are intriguing. While no experiment has definitively proven we're in a simulation, several have found anomalies that are difficult to explain with conventional physics. But here's the really mind-bending part. Even if these experiments prove we're in a simulation, what then? How would humanity react to discovering that everything we know is artificial? Let's imagine for a moment that tomorrow, scientists announce definitive proof that we're living in a computer simulation. How would this change everything? The immediate reaction would likely be chaos. Religious institutions would need to grapple with the implications for concepts of soul, afterlife, and divine creation. If we're simulated, are we real enough to have souls? Do simulated beings go to heaven? Philosophy would face a revolution. Questions about free will, consciousness, and the meaning of life would take on entirely new dimensions. If our choices are computed, do we really have free will? If our thoughts are simulated, are we truly conscious? The legal system would face unprecedented challenges. If nothing is real, in the traditional sense, how do we define rights, responsibilities, and justice? Are crimes against simulated beings still crimes? But perhaps more importantly, how would it affect individual human psychology? Some might find it liberating. If reality is artificial, perhaps death isn't final, perhaps suffering isn't real. Others might find it deeply disturbing. If nothing matters, why continue living? There's also the practical question. What could we do about it? If we're in a simulation, can we escape? Should we try to contact our simulators? Some theorists suggest that if we prove we're conscious and self-aware, our simulators might have ethical obligations to us. Elon Musk has suggested that if we're in a simulation, we should try to make it interesting. Perhaps our simulators would be more likely to keep us running if we provide entertainment value. But here's a different perspective. Maybe it doesn't matter. Whether we're in base reality or a simulation, our experiences are real to us. Love still feels like love. Beauty is still beautiful. And meaning can still be found in our relationships and achievements. Some philosophers argue that simulation theory is ultimately irrelevant to how we should live. A simulated life well lived is still a life well lived. The values that matter to us, compassion, creativity, growth, connection, don't become less important if they're computed rather than natural. And there's another possibility. Maybe being in a simulation makes us more significant, not less. If someone or something powerful enough to create universe-scale simulations chose to include us, perhaps we're more important than we realize. As we stand on the brink of potentially answering one of the most profound questions about the nature of reality, we're forced to confront what it means to be human, what it means to be real, and what it means to matter. So, are we living in a computer simulation? The honest answer is, we don't know yet. But the fact that we can even ask this question scientifically represents a remarkable moment in human history. Whether you find simulation theory compelling or absurd, it's forced us to think more deeply about consciousness, reality, and our place in the universe. It's pushed us to develop new experimental techniques and to question our most basic assumptions about existence. In a way, simulation theory represents the ultimate expression of human curiosity and ingenuity. We've become sophisticated enough to question not just our place in the universe, but the very nature of the universe itself. Over the next few years, experiments currently underway may provide clearer answers. We might discover definitive evidence that we're in a simulation, or we might find proof that we're in base reality. Either answer would be profound. What do you think? Are we living in a simulation? Have you experienced any glitches in the matrix that made you question reality? Let me know in the comments below. And don't forget to subscribe for more mind-bending explorations of science and philosophy. Remember, whether we're real or simulated, we're in this together. And that's what makes it all worthwhile.